So as you can see, these are all the different atoms in there. So we can actually use this to set up an input file for doing simulations. So we're actually going to set up just a simple input file that's going to go into QChem, which is the software you're using to do these simulations. Actually, a little cool fact, Eric Bergquist, a grad student in the lab, and Dr. Lambrick were both part of creating QChem. So, little fun fact. I said fun fact twice, so ignore me. We're actually going to type in up top here, $molecule. Next line, we're going to type in 0. All right, and then space 1. So it's for charge and multiplicity. And then we're going to type in on the bottom here, we're just going to keep these molecules right here. And then we're going to type $N for ending the molecule section. Then we're going to do $rem, and then we're going to do job type. Optimization, since we're doing a simple optimization here. And then we're going to do basis, which is 6-31G star. And then we're going to use the word method. It used to be exchange, and we're going to do B3LYP. So the charge, the multiplicity, the basis set, and the exchange function that you're going to use, so this basis and this method are really going to be based on your own independent project. You're going to have to select which one you want to use for the different accuracy you would want, the time cost that you have, so how much time you want to be spending on these calculations. And then you're going to type in $N. So again, this method right here, this basis set, are going to be chosen by you based on your own constraints that you want to set. And then this is just dependent on the molecule that you're doing calculations on. And then we're going to do Control X, and then we're going to say yes and save this right here, and press enter because that's the name we want to save it under. So we're actually going to go into the directory now. We don't need to, but it would just be easier, so we have to type less things. All right, so actually this nano ethanol.xyz, once you open it up, you can see that this is an input file. So we're going to exit. This is what we made before. So again, Control X is exit. I'm going to just move this file under a different file name, .in. So you can just see the name changed right there. If you want to rename it, you could do it that way. As you can see, we're at the ethanol instructional directory, and we're going to open this ethanol.in file. So we can submit this onto HTTP for calculations. Specifically, this input file would generate an optimized geometry, coordinates of an optimized geometry. I'm just going to show you that a little bit later. For now, I'm going to just show you how to set up different kinds of input files for different types of advanced calculations. So I'm just going to exit out of here by pressing Control X. So what I want to do is I'm going to copy this ethanol.in file into an ethanol frequency.in file. So when you can see that you have an ethanol.in file, which is the original file we just saw with the same content, and we have an identical copy, ethanol frequency.in, so which is the file we're going to open. We're going to do ethanol frequency.in. We're going to open this. So the first type of calculation I'm just going to help you set up is just a simple frequency calculation. So we're going to get the frequency, the different vibrational modes in the Raman spectra of this compound. So depending on what you do, for example, when I was looking at dihedral angles in glutamine, so for example, what I had to do was I had to convert this XYZ format of the molecule from the output file that was generated once I had submitted my calculations. So that optimized geometry from that submitted calculation and the output file from it, I took that and I converted it to a ZMAT form so I could set the dihedral angles as a variable and use a different script to generate all these different output files with the different input files with the different dihedral angles, and then I did the simulation on every single output file with a different angle, with that different dihedral angle. But let's just pretend this is an output file with an and this is an optimized geometry. So what we're going to do is we're going to want to do a frequency calculation on it to get the Raman vibrational modes. So again, we're going to leave this this molecule section the same. Again, you might possibly have to also change to ZMAT format, but we're leaving it like this for now. Alright, $rem. Job type will actually be changed, and it's going to be frequency, FREQ. So I'm going to write this line. This exclamation mark means that this line is commented out. It's not part of the command. If you wanted to get the intensity of the Raman peaks, you would do Raman true without this exclamation mark at the beginning. But we're just gonna, since we don't need the intensity calculations and it's too time costly, we're gonna not do those calculations. Again, we're gonna choose a basis set and a method, and then that is all we would need to do for our frequency calculation. And then $end. So we're going to do Control X, and we're going to save this. So that's one type of input file we would need. So I always like to just go back into the file and make sure that I saved. I'm slightly paranoid, so you don't need to do this. Alright, so that looks good. So we're going to exit here. Alright, so before, when I told you can use the up button to go into older commands so you don't have to type them, so I want to make another file. So this time I want to do frequency calculations. But since we've been doing them in gas phase, I would also like to do these calculations in aqueous water solution. I'm going to type in just AQ. All right. So then we're going to type in ls. It'll show you this file that was created. It's going to be identical to the ethanol.in file. So we're just going to ethanol. Oh, I didn't type in the right name, so that's why this empty file is showing up. Let's see what I typed in wrong. Oh, we forgot the .in. Alright, so again, we're going to just pretend this is the optimized geometry that we got from the output file. And we're going to use this, and we're going to type in some more stuff. So there's really two possible methods by which you can. There's an implicit form and an explicit form. I'm gonna show you the implicit form, which is just the assumption there's there's about infinite water molecules. So after you have your job type as frequency, right here. Again, if you wanted the intensity of the peaks, you would type in do ramen space true on the next line after job type. And then you're going to type in solvent method, and you're going to choose PCM, which is this implicit method. And then again, $n is here. And then you're going to do $solvent dielectric 78.39. It's for water, and $end. So you're going to exit out of here by pressing Control X and then saving this. So there is really only one more type of file I want to show you set up. This one's going to be actually a deuterated calculation. So if you were to want to deuterate some of the hydrogens in ethanol and do the calculations, this is how you would do it. So again, I'm going to go up in Command, so I don't have to type this whole thing again. You can do this aqueous, then you would do aqueous, and then I would do iso. So every file name is like very clear as to what is inside that specific file. So we're going to do .iso.in. Alright, so as you can see here, after this section, we can change it to frequency. Again, if you want to get the intensities, you do ramen space true. And then we're going to do isotope 1. I'm actually just simply setting up a deuterated calculation in gas phase in vacuum here. So I'm going to change the file name at the end. Alright. And then $isotope . So let's say you're deuterating 1 or 2. You're going to type in 2 if you're deuterating 2 hydrogens. If you're deuterating only 1, you're going to put 1. this just commented out the deuterate comment. And then since it's the first hydrogen right here, we're going to do 1. Just specific hydrogen we want deuterated. So if it was this one, since it's atom 3, we would put 3. And then we would do the mass of the deuterium. So 2.01410. And then we would go $end. Again, I didn't do these calculations aqueously, so I'm just going to do isotope. Okay, so you can really see the 4 types of calculations that we have set up. Simple frequency calculation in gas phase, simple frequency calculation in solution, specifically water in this case, done implicitly. Simple frequency calculation done on a compound with one of its hydrogens that is deuterated, and this is an optimization job. So again, I just really want to emphasize, I'm going to show you in a little bit how to submit all these calculations, but the coordinates or the XYZ files that we used in these frequency calculations should actually be obtained from the ethanol.out file that we would obtain after submitting this for calculations. I just want to show you how to delete this file, since it's not a type of calculation we're going to be doing. So you can just do RM, and then I'm just going to copy paste because it's quicker. You can type this whole thing in if you want, and that deletes the file and removes it. So if you type in ls again, it's gone.